This video is the second part of Chapter 9, Class 11th, Solar Radiation, Heat Balance and Temperature.
Now let's read about spatial distribution of insolation at the Earth's surface, meaning when the solar energy reaches the Earth's surface, what is the pattern and arrangement like? How is the heat spread across different regions of Earth? The amount of incoming solar energy received at the surface varies about 320 watt per meter square in the tropics to about 70 watt per meter square in the poles. So clearly the North and South Pole receive less solar energy. Or in other words, as we go away from the equator, the amount of solar energy falling on Earth's surface reduces. So 320 watts per meter square means the heat produced by 320 watts of light when falling on a square-shaped ground, with each side of length 1 meter. If I have to put it in perspective, then almost or a little bigger than a big-sized carom board. That much of surface area would be 1 meter square, and 320 watts would be 8 40-watt bulbs. So if you switch on 8 40 watts bulb and direct its lighting on a big-sized carom board, the amount of heat produced would be almost equivalent to the heat received at the surface of the Earth in the tropical region. So tropical region is the area around the equator between the Tropic of Cancer in the northern hemisphere and Tropic of Capricorn in the southern hemisphere. This one. Now here it says maximum insolation is received over the subtropical deserts, where the cloudiness is the least. So if you look at the world map, there are very few deserts in tropical region. Most of the deserts exist in subtropical, temperate and polar region. Basically, they are away from the equator. Just in case you must be wondering, why am I counting Antarctica and Arctic region as deserts? Then you must know that not every desert is hot. A desert is an area or region that receives extremely low amount of precipitation and it has minimal vegetation and very little fauna. So here it says, maximum insolation is received over the subtropical deserts. So subtropical region is this, and here we have deserts like Mojave, Sonoran, Chihuahua, Thar, Sahara and Great Victoria Desert. So here you see there are no clouds. Hence the amount of insolation received on the Earth's surface at these regions will be far more than tropical region. And the reason is simple again. The tropical region is warm and that creates moisture. Moisture converts into cloud and that's how rain occurs. So if there is cloud, it will reflect back good amount of incoming sunlight, and subtropical deserts do not have much clouds and it receives maximum amount of incoming solar energy. And I want you to always remember this point. Sky over the oceans are typically covered by clouds, whereas on land, that's not the case. Only if a landmass is closer to an ocean or sea, only then it has cloudy sky. If you remember this point, you will be able to easily figure out which place is cloudy and which is not. And the last point is, insolation is more over the continent than over the oceans. I think it is easy to understand this because of this picture. I hope you get it. Alright, let's go to the next topic, heating and cooling of atmosphere. Just a quick refresher, atmosphere has 5 layers, or some of you may call 4 layers, but I'm also counting exosphere. As you can see, exosphere is the first layer that gets the solar energy, and then the respective layers. So this way, the solar energy transmits the heat from exosphere to troposphere, from outside to inside. Now in between the troposphere and Earth's surface, we have some atmospheric gases, water vapor, clouds and ozone. So the solar energy comes in contact with the atmospheric gases, water vapor, clouds and ozone. While some energy is absorbed, some energy is also reflected back to space. And as the air which is in contact with the land gets heated up, the surface of Earth gets ultimately heated up. Now you see all the layers of the atmosphere and the air in contact with the land all gets heated one after another. This process is called conduction, similar to your handle that you have on your cooking utensil. The moment the utensil gets heated, slowly you will feel the heat being transmitted to the handle. So this is called conduction. So it is conduction that is heating the surface of the Earth step by step. I hope so far it's clear. One more thing you need to understand is that the Earth's surface on which we stand gets the heat from 2 sources. One, as we know, it's through the sun rays, and the other source is Earth's core. So now you are totally aware of the heating pattern of the Earth's surface. Now this air which is in contact with the Earth, In other words, the air that is around us, it is warm, and warm air rises vertically, that is straight up. Now as it goes up, it comes in contact with the atmosphere, that is the troposphere. Now this process of vertical heating of the atmosphere is known as convection. Remember this term. On the other hand, the transfer of heat through horizontal movement of air is called advection. Now you have to remember these two terms, advection and convection. One goes straight up and the other goes sideways. This sideways movement of warm air is a little important. You see, the movement of warm air is what affects the temperature of a region. You see, in middle latitudes, most of the weather and temperature variation during day and night is caused by horizontal movement of winds, that is advection. You must have also heard, especially in northern India, about this local wind that blows during summer season. It's called Loo. It's warm dry wind, basically a result of advection process, horizontal movement of air. Now let's move on to the next topic, terrestrial radiation. The meaning of the word terrestrial is land, and radiation means emission of energy. Here we are referring to heat energy. So terrestrial radiation means Earth's heat energy. We have read how sun rays enters the atmosphere and then heats up the Earth's surface. And the solar energy that comes in, it comes in short waves form. Because Earth's atmosphere filters most of the harmful rays that comes in. Hence the incoming solar energy comes in short wave forms and they heats up the land surface. Now in return, the land surface, which is hot and warm, it radiates heat. So how does a warm body becomes cool? By radiating the heat, right? Similarly, the warm land surface radiates heat. Now this energy which has been radiated is in long wave form. So always remember this point. Incoming solar energy is in short wave form and outgoing radiating heat is in long wave form. Now this radiating heat that goes up in the air vertically and it touches the atmosphere. So if you try to observe, first the sun rays touches the atmosphere and then gets inside. Basically it's incoming. So if you treat the exosphere as the first and topmost layer of the atmosphere, then troposphere becomes the bottom or the lowest layer of the atmosphere. Now the earth, after being heated itself, becomes a radiating body and it radiates energy back to the atmosphere. So you see, warm air is going up vertically. It is now going to touch the bottom layer of the atmosphere. In other words, this radiating energy heats up the atmosphere from below. This process is known as terrestrial radiation. Now as soon as it touches the lower layer of the atmosphere, which is the troposphere, the long wave radiation is absorbed by the atmospheric gases, particularly by carbon dioxide and the other greenhouse gases like methane, nitrous oxide, ozone, etc. Now try to understand this. If you cover a utensil that has hot boiled water with a lid, then naturally it will increase the temperature inside the utensil, right? Similarly, if the atmosphere has large percentage of carbon and other greenhouse gas molecules, then it blocks the Earth's heat from going out in the space. Which is good to some extent because we need some heat, otherwise everything will freeze up on Earth. However, excessive heat can increase the global temperature of Earth, and that's what leads to global warming and climate change. So I hope you understood what is terrestrial radiation and how the atmosphere is indirectly heated by the Earth's radiation. Now let's go to the next topic, heat budget of the planet Earth. Now by the term heat budget, you can easily relate that it is referring to the balance between incoming heat absorbed by the Earth and the outgoing heat escaping it in the form of radiation. And if this balance is disturbed, then Earth would get progressively warmer or cooler with each passing year. Let me illustrate with an example. Let's assume that the amount of incoming solar energy at the top of the atmosphere is 100%, which means 100% of sun rays are hitting the exosphere, the first and the outermost layer of the atmosphere. Now, while passing through the layers of atmosphere, some amount of energy is reflected, scattered and absorbed, and only the remaining part reaches the Earth's surface. So 35% of sun rays are reflected back to space, even before reaching the Earth's surface. So this 35% of reflected radiation is called albedo of the Earth. In other words, albedo means how much of the sun's energy is reflected back into space. Now, as the remaining 65% sun rays enters the atmosphere, 14% of it is absorbed within the atmosphere by water vapor, dust particles and other atmospheric gases. Now, the remaining 51% of sun rays is actually absorbed by the Earth's surface. I hope till here it is clear. Now it's time for the Earth to radiate back the 51% of heat which is received from the Sun. In other words, it's time for terrestrial radiation. So this time the heat travels in vertical manner and there is a term given to it. It's called convection. So as the heat rises, 34% of the heat will be absorbed again by the atmosphere, which includes water vapor, dust particles, horizontal air movement and other atmospheric gases. The remaining 17% of the heat is radiated to space directly. If you notice, in total 48% of heat is absorbed by the atmosphere, that is 34% from terrestrial radiation and 14% from incoming solar energy. And this 48% of heat absorbed by the atmosphere is also radiated back into space. Now the total radiation is 48 plus 17 is equal to 65%. And if you remember in the beginning, we saw that 65% of heat makes it into the atmosphere. So what we can conclude from this calculation is that if the amount of heat received in the form of insolation equals the amount lost by the Earth through terrestrial radiation, which in this case we found it to be equal, that means the Earth maintains its temperature. Or in other words, the Earth neither warms up too much nor cools down too much, despite the huge transfer of heat that takes place. Now we will look at the variation in the net heat budget at the Earth's surface. It is a known fact that not every place on Earth receives equal amount of solar energy. I mean, we have read that as we go away from the equator, both in northern as well as southern hemisphere, the temperature decreases. The same is highlighted here in this figure 9.3. On the x-axis, we have latitude ranging from north to south. And on y-axis, we have the incoming solar energy in watts. As you can see, the 0 degree is the equator. And as we go towards left or right, we can see that the graph is going down, which means as we go away from the equator, both in northern as well as southern hemisphere, the temperature decreases. You see the incoming solar radiation decreases, but if you look at the terrestrial radiation, which is the heat that the Earth radiates, that one is a little higher than incoming solar radiation. And the reason behind that is, if you see above 60 degrees, Arctic and Antarctic region starts, and it's all ice there. So that ice is white, and that reflects good amount of sun rays back to the atmosphere. That's the reason we see this terrestrial radiation curve much wider than the solar radiation curve. So this is all about the latitudinal variation in net radiation balance. Now we move on to the topic factors that control the temperature distribution on Earth. As we know, not every place on Earth has similar kind of weather or temperature. So it is important to know the factors that lead to such a phenomena. The first one is the latitude of the place. Now temperature on Earth decreases as we go away from the equator. So here is the equatorial region, which is also known as tropical region. Then we have the middle latitude, which is called the temperate region. And finally we have frigid zone by the name of Arctic Circle in the north and Antarctic Circle in south. Now the reason there is a variation in temperature based on latitude is because the incoming solar energy is direct and higher at the equatorial region. And as we go towards the poles, the sun rays are at lower angle. The second factor is the altitude. During terrestrial radiation, that is when the Earth's surface radiates heat, in the process the atmosphere gets indirectly heated from below. The warm air in the form of long wave travels vertically towards the troposphere, making the atmosphere warm from below. This process is also called as convection process. Now that you understand this mechanism, you need to understand this that the places near the sea level record higher temperature than the places situated at higher elevations. Because if a place is nearer to the sea level, the air in that region contains a lot of moisture. And moisture is a direct outcome of evaporation. That means this region has to be warmer. Now as air rises, the pressure decreases. It is this low pressure at high altitudes that causes the temperature to be colder on top of a mountain than at sea level. In other words, the temperature generally decreases with increasing height. And just remember this term. The rate of decrease of temperature with height is termed as the normal lapse rate. The third factor is distance from the sea. Another factor that influences the temperature is the location of a place with respect to the sea. Compared to the land, the sea gets heated slowly and loses heat slowly. Land heats up and cools down quickly. Therefore, the variation in temperature over the sea is less compared to land. That's why coastal regions barely face any variation in temperature. The temperature is almost same throughout the day. And the fourth factor is air mass and ocean currents. Now it is a well-known fact that temperature changes due to movement of air mass. If the air is warm, then the region that receives that warm air will have warm temperature. And similarly, if the air is cool, then the region that receives the cool air will have cooler temperature. Now the places that are nearer to warmer ocean currents will have higher temperature. Have a look at this map. The red arrows depicts warm ocean currents and the blue one depict cold ocean currents. So the places where you see red arrows have warm ocean currents that widely affects the temperature of the nearby landmass. And just a general information, the places where cold and warm ocean current meets, that place is usually a major fishing grounds of the world. Now let's finish the last topic of this chapter, distribution of temperature. First of all, let me tell you what is isotherm. It is a line on a map connecting points having the same temperature at a given time. Basically, they are lines of equal temperature. They are used to map the geographic pattern of temperature across the Earth's surface. So when you look at this map, these irregular lines that you see, let's take this particular line. This is of 20 degrees Celsius. Now this line passes through Mexico, Cuba, then through Atlantic Ocean it goes to the central countries in Africa like Mali, Niger, Chad, Sudan. Then this line goes to Saudi Arabia, from there to central region of India. So basically all these places will have 20 degrees Celsius at one given point of time. This is what this line, which is called isotherm, implies. Okay, great. Now that you know what is an isotherm, now let's try to understand the global distribution of temperature. In other words, why do isotherms shift north and south from season to season? So this is the equator. Above the equator we have northern hemisphere and below is southern hemisphere. And we already know that as we go away from the equator towards the poles, temperature decreases. Now when you look at this world map, you see there is more land surface area in northern hemisphere when compared to southern hemisphere. And you can also see that these irregular lines, that is the isotherms, they run parallel to the latitude, right? Now this deviation in the line, that is the change in the shape of isotherms, happens especially in the month of January and July. You see, in the month of January, the isotherms over the continents bend towards south, while the isotherms on ocean bend towards north. And this is due to the differential heating and cooling pattern of land and ocean. You see, always remember, land heats faster as well as cools off faster than water. In the month of January, the Earth's northern hemisphere is tilted away from the sun, making the southern hemisphere exposed more to the sun rays. Basically, it's winter in northern hemisphere. So this way, the water in the South Atlantic and Pacific is absorbing greater amount of energy during January. That is why you see the isotherms on northern Atlantic Ocean bend towards the north, because warm ocean currents are moving towards the colder region. If we look at the isotherms on land, you see the land is cool. As I said, land cools off faster than ocean. That's why the isotherms on land bend towards south. It is just like birds. The isotherms head to south where it's warm. Now if you look at the southern hemisphere, you will not see much of deviation in southern isotherms. You can only see a little deviation over land region, especially near South America, South Africa, because again the logic is that the entire southern hemisphere is receiving more sun rays than the northern hemisphere in January. So naturally the land's heat will head towards equator. That's why you see in some places the isotherms slightly bend towards the north. Otherwise in ocean region, the isotherm is almost a straight line. Now similarly in the month of July, the northern hemisphere is tilted towards the sun. And it is summer in northern hemisphere and winter in southern hemisphere. So everything that I just explained turns opposite. You will see less bends in the isotherms of northern hemisphere. You will see some bends in the temperate region and Arctic region, since these two places are cooler as the angle of sun rays are low in these regions. So here you will see a little deviation of the isotherms towards the south. In the southern hemisphere, it's as usual how it is during the month of January, primarily because there is less land surface area in the southern hemisphere. So this was all about the distribution pattern of temperature on the Earth's surface. With this, we have come to an end of this chapter. I hope you have understood this chapter and found this video useful. Thanks for watching, and I'll see you in the next one.